Hello, everyone. My name is Jess Nassery. I am an associate professor of politics and international affairs here at Wake Forest University. Welcome to the International Methods Colloquium. The IMC is a periodic, online, interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Wake Forest University and by Springer Publishing. This week's speaker is Pedro Rodriguez from Vanderbilt University, giving a talk entitled Embedding Regression, Models for Context-Specific Description and Inference in Social Science. The talk will last between 30 to 40 minutes, after which point we will take questions. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window, and you can ask a question at any time, but we will hold the questions until the end of the talk. If you want to be recognized and ask your question via audio, please indicate this in the Q&A text box and I can unmute you. Otherwise, I will read your question aloud during the Q&A period. A link to the paper and the slides will be available in the Zoom webinar chat window so that you can refer to it throughout the presentation. Now I'd like to welcome Pedro Rodriguez to the IMC. Welcome, Pedro.
Great. Thank you, Justin. Thank you again for the invitation and for organizing this. And thank you all for being here. Really looking forward to your feedback and questions on what is still an ongoing project. So today I'll be talking to you about embedding regression. This is joint work, I should say, with Arthur Sperling at NYU and Brandon Stewart at Princeton University. So let me begin first with a thought experiment. Suppose that you had never heard of the word migrant before, and you encountered the word for the first time reading Fox News headlines such as the following, where migrant appears in the context of such words as drug cartels, crisis, forced entry of property, national security and health crises, change the country forever, and so forth. The question is, what do you infer about the meaning of the word migrant from these headlines? Now, suppose that instead of Fox News headlines, you had encountered the word for the first time reading CBS News headlines, where the word migrant appears in such contexts as refugee agency, migrant children, bed space, unaccompanied minors, family reunions, desperate migrants, and so forth. Again, the question being, what do you infer about the meaning of the word migrant in this case? And importantly, how different is it from the inferences that you drew based on the Fox News headlines, right? So this thought experiment is illustrative of a broader research problem or objective that we have as political scientists and social scientists more broadly, which is that we want to quantify systematic differences in meaning across groups and time and get measures of the associated uncertainty. For all intents and purposes, we want semantic regression, something like a multiple regression where we can regress the meaning of a term, in our example, migrant, on a series of covariates. So here, migrant I is a mention of the word, of the term that we're interested in our corpus, in our corpus of headlines in our example, and the X's are just covariates, for example, capturing group membership. Again, in our example, this could be the news source from whence the headline came. But the problem is that this presupposes, right, our ability to do this semantic regression presupposes that we can numerically represent each individual instance of the target word, in our case, migrant I, in our corpus, right, in a way that captures variation in meaning. And this is generally very challenging to do. So our solution in this project and our contribution is we leverage pre-trained word embeddings. Specifically, we place Kodak et al.'s 2018 innovation, a la carte embeddings, within a regression framework, one that is transparent, efficient, and computationally simple, allows us to evaluate hypotheses about covariate effects on embeddings, performs well in the cases of rare words or small corpora, which is often the case for us in political science and social science more broadly, where we can't always rely on huge data sets, provides more accurate and interpretable results than competing methods, while also being faster to run and more numerically stable. Now, I should briefly say that my co-author in this project, Brandon Stewart, is also a co-author in Kodak et al. 2018. So this is building on that work. So the outline of the presentation today. I'll first introduce word embeddings for those that aren't yet familiar with word embeddings. I'll then build on word embeddings to introduce an apparently intuitive solution to the problem that I just laid out. I'll then go on to introduce Kodak et al.'s 2018 innovation, a la carte embeddings, and then show how we insert this framework within a regression framework, followed by a couple of political science applications. And then finally, I'll conclude by just briefly introducing an R package that we built based on this project that allows you to run these types of regressions yourself. So hopefully the slides now work. So I'll start with word embeddings, a brief introduction. So word embeddings, as I mentioned, are part of the distributional semantic model family, and as such are grounded on the distributional hypothesis, here captured by first quote, "You shall know a word by the company it keeps." In other words, we can learn something about the meaning of a word from the contexts within which it appears, and words that appear in similar contexts will tend to be semantically related. So let's take a toy example just to illustrate how what word embeddings are and how we estimate them. So given a training corpus, what we want to do is we want to map our vocabulary onto a common space, right? So in this toy example, the space is two-dimensional. Usually the dimensionality of the space is going to range anywhere from 50 to a couple of hundred dimensions, but to keep it simple here, we have 2 dimensions. Our vocabulary here consists of these 3 words, coffee, cup, and tea. And the way that we initialize the model is just randomly scattering these words in the semantic space, on the embedding space. And then we provided instances of these words being used in context in order to train the model. So for example, our first instance from our hypothetical corpus is I had a cup of coffee this morning, the target word here being coffee. And then we define a context around this target word. In this case, usually it's going to be a symmetric window. In this case, it's going to be two words preceding and after the target word. And the model then is trained to learn to assign high probabilities to the words that appear within the context of the target word. So it sees, for example, here that cup appears in the context of coffee. And so it wants to assign it a high probability. And in order to do that, it learns to essentially changes the numeric representation of the 2 words, moving them closer together in this space. Mathematically, what's going here underneath is essentially that probability is going to be based on the inner product of these 2 vectors. And so the closer they are, the higher the inner product of these 2 vectors. So we show our model another instance of another word in our vocabulary here, tea. Again, a context window, local window around the target word, tea. And it sees again that cup is within the context of tea. And so again, it wants to assign it a higher probability. And so it changes the numeric representation of these vectors, moving them closer together. And so tea moves closer to cup. Notice that tea not only moves closer to cup, but also moves closer to coffee. So it's not only about co-occurrence, but actually about appearing in similar contexts, such as the case of coffee and tea. So ultimately, at the end of this training model, after providing a lot of instances of all the words in our vocabulary used in context, we end up with all the words in the vocabulary mapped onto this common multidimensional space here, in this case, 2-dimensional space, wherein distance in this space is informative of the semantic relationship between these words. Words that are closer together are going to be more semantically related than words that are further apart. So we can either train an embedding model ourselves. So for example, if we have a large enough corpus, we can train our local embeddings model on this corpus, or we can often, as we often do, rely on just simply downloading pre-trained embedding models trained on very large online corpora, such as the Stanford Glove 300, which is just easily downloadable from online and has been trained on the Wikipedia and GigaWord corpora, right? In a different paper, we showed that these pre-trained embeddings work rather well with political science corpus, such that you don't always need to train your own set of embeddings. So an intuitive solution, right? So we've essentially mapped a vocabulary onto a common space. When we have these pre-trained embeddings, we have them all mapped into a common space. So an intuitive solution to numerically represent an instance of a word in our corpus is to average the pre-trained embeddings of the surrounding words, right? So if we have an instance, say for example, we take one of our headlines that we introduced on our thought experiment at the beginning, migrant is the first instance. We take a context around migrant, of this first instance of migrant. We find from our pre-trained embeddings, we find the embeddings of each of these words, right? Again, these are going to be D, in this case, they're going to be 300 dimensional, D-dimensional representations of each of these words. And we simply collapse these and average these, so column average of these. And that gives us a representation for that instance of the word migrant in our corpus. To get an average representation of the target word for our corpus for the set of headlines, we can simply average the representations of all those single individual instances, right? So we can simply do something like this, where we have a representation for migrant 1, 2, and 3, and we simply average across all the instances of that word in our corpus, and that gives us an embedding for that word, right? So we get that numeric representation both at the instance level and at the corpus level. The question is, right, so we wanted to achieve this. So the question is whether this numeric representation actually works. And unfortunately, that doesn't really work all that well, right? So it turns out that word embeddings share these common but uninformative directions that when you average them, these directions are augmented. And what ultimately ends up happening is that the embedding, that averaged embedding, ends up in a semantically uninformative area of the embedding space. And it'll become clear what I mean by semantically uninformative in a couple of slides in an example. So we turn to Aurora et al. 2018 and subsequently Kodak et al. 2018. So let's start with Aurora et al. 2018. And the key theoretical result here is that given a corpus and its corresponding embeddings, in other words, embeddings trained on this corpus, there exists a linear relationship between the embedding of a word, so the embedding again trained on the full corpus, right? And the average of the embeddings of its contexts in the corresponding corpus, right? So we have VW is that embedding trained on the full corpus. And then what we can do is we can estimate another type of embedding by simply taking our corpus, finding all the instances for a given word in which that word appears, take the contexts of all those instances, find the embeddings for those, just what we did in the example, find the embeddings of those, average those, and create a new embedding for that word, right? And so we're comparing those two types of embeddings. And what Aurora 2018 show is that there exists a linear relationship between those two, right? Specified by this square matrix A, right? Well, the square matrix A is, well, I'll show you shortly, is D by D dimensional. In other words, D being the dimensionality of the embedding space. To learn A, we have given a corpus and its corresponding embeddings, again, embeddings trained on that corpus. A can be learned via the following linear regression model that essentially minimizes the distance between those embeddings trained on the full corpus, just using the embeddings model, normal embeddings model, and then those embeddings trained by, again, finding all the instances of all the words in all the instances of a word in the corpus, finding the context, averaging all the embeddings of those contexts, and essentially that difference is the one that we want to minimize, right? And we minimize it by defining A, by optimizing for A. So in English, again, the linear relation, A is that linear relationship that minimizes the difference between the pre-trained embeddings and the average of the embeddings of the contexts. So that VW and that UW. Okay. So A only needs to be estimated once for a given corpus and a corresponding embeddings. Right. So once we estimate that A, we can essentially estimate these context-based embeddings easily. And that's what Kodak et al. 2018 do, right? So they say essentially, given an embedding based on Aurora et al. 2018, we can say that given an embedding model and its corresponding transformation matrix A, we can embed a new unseen target word, so an embedding for which we don't have an embedding in the embedding model, right? Simply, if we have data, simply by finding all the instances in which that word appears, finding all the context, and just, again, averaging the embeddings of those contexts, words, and then multiplying by that transformation matrix. And voila, you have an embedding a la carte, hence the name. So just to provide a more intuitive explanation of this, let's go back to our example. We had this instance of the word migrant migrant 1, right? We take the context, around this target word, right? Again, using the pre-trained embeddings, we find the embeddings for those context words around lie grid 1. We average those, and that gives us that average context embedding. The average representation of the target word for our corpus just averages all those individual single instance embeddings. Right? So we showed that before, or we did this before. Now to get the a la carte embedding, it's just one more step, which is multiplying that average by this transformation matrix A, right? So we have this, we simply multiply by that transformation matrix A to get the a la carte embedding, right? Notice that since A is a constant, we can move this A inside the sum or inside the expectation. And essentially we can talk about averaging over single instance a la carte embeddings. So does this work? It turns out that it works rather well, right? So let's show you an example, an actual estimated example. So we're going to take a corpus of New York Times where we have multiple instances of Trump with uppercase T, the name, and Trump with lowercase t. And we sample 100 random instances of both of these senses of the word Trump, right? These two different senses of the word Trump. And we embed them using a la carte, the process that I just described, for each one of these instances. And the question is, can we distinguish between the two senses of the word? So we're embedding each individual instance separately. And the question is, can we distinguish between the two senses of the word Trump, right? As embeddings, we're going to be using pre-trained, so Stanford Glove 300. And the transformation matrix that we're going to use is that estimated in Kodak et al. That is specific to the Stanford Glove 300. Right? So this is a 300-dimensional embedding space, but we use principal component to reduce it to the first two, to reduce the dimensionality for visualization purposes. And so we start essentially embedding each of these instances. Let's take one instance of the word Trump with uppercase T. We embed it using a la carte. We map it on here, and we see essentially again just mapped onto the space. We take another instance of the word Trump. Again, what we're doing here for the a la carte embedding is just finding all the embeddings of the surrounding words of Trump, averaging those and multiplying it by this A transformation matrix. So we map it here. We do the same with lowercase t Trump. It is in a separate part of the space. It ends up in a separate part of the space. We do it with all the 100 randomly sampled instances. And we see that we do get, even with these single instance embeddings, right, we get this meaningful separation of the two senses, right? Now, to get the average a la carte, or to get the a la carte embedding for the two groups, we can simply average all these single instance embeddings and create one embedding for each group or for each sense of the word, which we can then use to find nearest neighbors. For those of you who aren't familiar with word embeddings, nearest neighbors are essentially given an embedding for a word. What we're doing, the top 10 nearest neighbors are just the top 10 words that are closest to that word on the embedding space. So I'm going to show you first the top 10 nearest neighbors for the transformed, essentially when we do a la carte embedding of the single instances, and I'll compare it to the untransformed. What that first intuitive solution that I showed that didn't really work out, I'll show you what happens if you don't actually do the transformation. So when you do the transformation of these a la carte embeddings, then you get meaningful nearest neighbors, essentially Trump uppercase T being associated with former President Trump, Trump with lowercase t associated with a card game. If you don't do the transformation, if you stay to that first step, which is averaging over the context words, you end up with stopwords as nearest neighbors. So this is what I meant when I said that just averaging context embeddings and using that as a numeric representation of your word lands you on a semantically uninformative part of the space. This is exactly what I mean. So that transformation is key. So now let's go, that's the key component and what we want to do now, this a la carte embeddings, and what we want to do now is insert this within a regression framework. So notice that we've essentially been talking about expectations. We've been talking about conditional expectations already because we've been taking the expectation conditional on one sense of the word versus another. And so really it's just a regression framework is just a stone throw away, right? So suppose we're comparing the usage of a word by two different groups of people, group B and group C, right? Our model is the following, where yi is a 1 by d dimensional vector representing the a la carte embedding of that instance I of the word, right? So this is going to be a multivariate regression. So our dependent variable is the a la carte embedding of that single instance, right? So that collection of single instance embeddings. Notice, of course, the coefficients are going to be then also d-dimensional, d again being the dimensionality of the embedding space that you're using. And the X in this case, this is going to be an indicator variable capturing group membership. So equal to 1 if I is a member of group B, if instance I is a group member of group B, and 0 if it's group member of group C. So we then have, if we run this regression, take the expectations, we have that the coefficients, the estimated coefficients are just going to be averaging conditional on the values of X's, right? So the alpha hat is just going to be essentially taking the expectation over all the single instance a la carte embeddings when X is equal to 0, right? Again, we can take that A out as just the constant of that expectation. And that essentially is just equivalent to the a la carte embedding for when X is equal to 0. That is for when the instance is a member of group C. And then alpha hat plus beta hat is going to be the a la carte embedding for when X is equal to 1. So for when the instance is a member of group B. So our coefficients are essentially going to be the a la carte embeddings, right? And we can start talking about differences in meaning, right, between the use of the terms between these two groups by looking at these coefficients. So the way that we summarize the magnitude of the shift, right? So here the difference between the two groups is essentially beta hat, right? So the way that we summarize the magnitude of the shift, the semantic shift, is captured by using the norm of the beta hat coefficient. Right? This is just a nice way of summarizing the magnitude. A higher norm means a larger shift, semantic shift. These are usually best interpreted relative to some other shift, right? So just the norm by itself, just one coefficient, isn't necessarily all that informative. So usually what you want to do is to compare it to something else. So for example, you want to compare it to the shift difference between group B and group C for one word versus another word, or between group C and group D versus group D and group B. In other words, these norms are really more best interpreted in a relative sense. Since this is very computationally efficient, right? It's just matrix multiplications here. We can use bootstrapping very easily and very fast. So essentially bootstrapping here to quantify sampling variance, right? So the bootstrapping here is just simply sampling from our set of instances from each group, but with replacement and then running these regressions, right? And so that allows us to essentially estimate a confidence interval around these coefficients. And we can use permutation tests for inference, right? So what we can do is we randomize group assignment and run these regressions. And that allows us to estimate a null with which to make inference tests, right? So let's look at some applications. So suppose that you have the congressional record corpus and you want to essentially see differences in the meaning or the meaning and use of terms of a certain set of terms, right? And you want to compare the role of partisanship versus the role of gender, right? Our corpus is going to be the congressional record, sessions 111 to 114. These are the Obama years. Our embeddings, again, we're going to use these that we just download from online, the Stanford GloVe 300. And we're going to use Kodak et al.'s transformation matrix, again, that is specific to those set of embeddings. And as target words, we're going to use immigration, marriage, abortion. These are 3 politically charged terms. And then as controls, a comparison, we're going to use 3 stop words, right? So our priors here is that there aren't going to be any real semantic shifts or differences in stop words, neither in terms of partisanship or gender, right? But we do expect significant differences in the politically charged terms. And our model is simple. So it's just, again, this multivariate regression model where Republican is equal to 1 if the instance was mentioned by a Republican representative, 0 if it was mentioned by a Democrat representative, and then female corresponds to the gender assignment in the congressional record corpus. So equal to 1 if assigned female, equal to 0 if identified as male. So we're going to be plotting here the norm of the beta hat. So recall that beta hat is going to be the shift, that difference between one group and the other. So that semantic shift. And we just take the norm as a way of capturing this in a way that is easily summarized and visualizable and visualized. For a higher norm is, of course, a larger shift, right? So higher values here means larger semantic shift. So let's start with the stop words as a function of gender covariate. Again, these are really best interpreted by comparison to something else. So if we compare here the shift as a function of both gender and party, we see that there really isn't that much of a difference between the two. So that's consistent with our priors, that we really shouldn't see much of a difference in terms of these shifts as a function of gender or party when it comes to stop words. If we look at political terms, we see that the shift now is much larger as a function of gender, right? So much larger than with stop words, again, consistent with our priors. And then finally, if we look at it with respect to party, we see a much larger shift, much larger norms, right? So again, consistent with our expectations, there aren't really all that significant shifts in terms of when it comes to stop words, again, between Republicans and Democrats or within gender or between genders, but we do see these shifts for politically charged terms, with the largest shift being with immigration, right? With the term, the largest, at least in some partisan shift being in terms of immigration. We can look at nearest neighbors, right? And what we do here, since our framework is so flexible, what we can do is, given the embeddings for each of these groups, we're going to focus on the term immigration. We're going to focus on the partisan differences, so Democrats versus Republicans. And what we can do is we take the ratio, we find all the set of nearest neighbors. So we find the unit of the top 20 nearest neighbors for both groups. And then we find the ratio of the cosine similarity between those nearest neighbors and each group's embedding for the word immigration, again, computed using our regression framework. So since Republican here is the numerator, anything above 1 is going to be more a nearest neighbor closer to the Republican sense of the word. Anything below 1 is going to be a nearest neighbor closer to the Democrat sense of the word. And the y-axis here is just ranking how distinctive this is or partisan this is in terms of relative to all the other words. So lower values here means more distinctive. It'll be clear shortly. So if we look at so again, left more Democrat, right more Republican. These are the shared top 20 nearest neighbors, right? So these are the top nearest neighbors that were shared by both groups. And then we find the nearest neighbors that were specific only to Democrats. And then when we compute, as is logical, when we compute the cosine similarity ratio of those nearest neighbors with respect to both embeddings, we find that these are much more to the left, so much more specific to the Democrat sense of the word. And then we can do the same for Republicans, and we see these are specific to the Republican side with, again, further down the line, this partisan rank or higher up in terms of getting close to 1, these are more distinctive terms, right? So what we see here in a qualitative sense is that Democrats are focusing much more on reform and overhauling the system and modernizing the system, whereas Republicans are focusing much more on the enforcement of immigration laws. Again, our framework, since it's so computationally pretty easy to implement, we can do also permutation type inference for nearest neighbors, where we just randomize the assignment of group assignment, and then we can compute exactly these types of ratios in order to see which are significant and which aren't. These are the stars. Those that are significant are symbolized with a star here. So our framework allows us also to add both confidence intervals and inference to nearest neighbors. So let's take another example here, the meaning of empire. We want to see how the meaning of empire changed, or the distance in the meaning of empire shifted between British parliamentarians and American representatives. So our corpus is going to consist of the full congressional record corpus from 1935 to 2010, and the Hansard, that's parliamentary speeches corpus from 35 to 2010. We're going to be, instead of using pre-trained embeddings, we're going to be estimating our own embeddings. We have a very large corpus, and it's likely that pre-trained embeddings don't, these glove embeddings don't adjust all that well to language from 1935. We're actually going to be training our own embeddings on this corpus and estimating our own transformation, so specific to these embeddings, transformation matrix. And the target word in this case is empire. Here, the indicator variable is going to be American, which is equal to 1 if it's an instance from the American corpus and 0 otherwise. We're going to be estimating this model separately for each year, right? So estimating this coefficient for each year, and we can map this over time. Again, the y-axis is norm of beta hat, that shift. So the larger the shift, the larger the norm, the larger the shift, the larger the difference in the senses of the words between these two groups. This is the evolution of that difference over time. We run a structural test model, a structural break test, where we find that 47, 48 is where the break lies. And if we look, so where really there was a big shift in the usage and the difference between the usage of the term. And if we look at the nearest neighbors, using the same process that I described before, we find, sorry, for 1940, these are the nearest neighbors of the meaning of empire for 47, so pre-4748, pre that structural break. So we see that there's a lot of shared nearest neighbors. The difference lying in, and the American representatives are speaking more about Japanese and European empires here, whereas the British are talking about their own sort of territories and Africa and the Commonwealth. If we look past the structural break, so the nearest neighbors of all those instances after the structural break, we see that the big difference lies, one, there's no shared nearest neighbors. So there's a big gap. There's no, when we find the nearest neighbors for the two census, none of them are shared. But two, the big difference lies in that the British still talk about their Commonwealth and their colonies and whatnot, or the Commonwealth later on, after the termination of the empire. And then American representatives are talking about communism and the Soviet empire, right? So that the Americans shifted rather rapidly after the end of the Second World War towards talking about communism, whereas the British continued to talk about their own sort of Commonwealth. A final application that is slightly different from these two is survey openings, right? So our corpus is the ANES 2016, the open-ended responses to the question ANES 2016, in which they ask the respondents to list the most important problems facing the country, right? So these are just open-ended responses. The embeddings that we're going to use are Stanford Glove 300. The transformation matrix, so again, those pre-trained embeddings. I'm going to use the transformation matrix specific to those embeddings. And notice here, the target text is not a word. It's going to be the full response, right? So we're not going to be looking at the context around the given word, but rather we're going to embed using a la carte the full response for each individual respondent, right? So that's going to be our YI in this case. And we're just going to use some covariates captured in the survey as well. So just gender-related covariates and ideology-related covariates. So again, we look at the norm of beta hat as a way of summarizing that shift, that semantic shift. The higher the norm, the larger the shift. If we look at differences in gender, so the alpha here I should note, is essentially female Democrat, right? So these are, that's the constant here, what the constant is capturing here. So these are relative to that. So here we have the shift. It's significant relative to, again, based on our permutation test, relative to that constant. This is the coefficient on moderate, again, larger, so consistent with, I believe, our standard priors, our prior should be here, is that ideology should imply larger shift. There's larger differences across ideology than across gender. And finally, with conservative, there's a much larger shift than even just with moderates. So this is consistent again with our priors that there's a bigger difference between liberals and conservatives than between moderates and liberals. Sorry. So we can look at nearest neighbors again, just to do some sort of more qualitative interpretation of these results. We have some shared nearest neighbors to these two census, well, embeddings of the open-ended responses. We have some that are specific to liberal and some that are specific to conservatives. We can see here that liberals focus much more on inequality and injustice, and racism and intolerance and so forth, whereas conservatives focus much more on jobs. This is in 2016. On jobs and of course the big distinguishing trait being immigration-related issues. Right? So we put all of this framework in order to make it easy for you to implement it within our package. We tried to follow the linear LM and GLM syntax in terms of operators. So the main function in our package looks something like this. You have a bunch of options, but essentially you specify the formula where you have the meaning, the term that you're interested, the target term, and then the covariates. These are the indicator variables, and then you specify your corpus and whether you bootstrap or do permutation test and so forth, right? So this should allow you to very easily do your own semantic or embedding regressions. So to conclude, the problem that I motivated this presentation with and that motivates the project is that we want to quantify systematic differences in meaning across groups and time and get measures of the associated uncertainty. And our contribution, or solution, is that we place Kodak et al.'s 2018 innovation, a la carte embeddings, within a regression framework and specifically one that allows us to run semantic regressions or embedding regressions of the form where you can regress the sense of a term on a series of covariates, right? That allows you to get at this, essentially quantifying the differences in meaning across groups and time and get a measure of associated uncertainty. I should say that while we use a la carte embeddings as a way of creating those numeric representations of these single instances, you can also use other methods to the extent that you can show that those actually do capture variation in meaning, right? And with that, I conclude. The paper is available on my GitHub, and the package context is also available on my GitHub. And I'm, again, thankful, Justin, for the invitation and looking forward to your questions.
Thank you very much for that presentation, Pedro. At this point, Pedro Rodriguez is available to take questions from the audience. We already have quite a few questions lined up. If you wish to be recognized and ask your question via audio, please indicate this in the Q&A text box. Otherwise, I will read your question during the Q&A period. I'll just start at the beginning. Johan Ortega asks, first, is it possible to locally train this algorithm in Spanish? And second, should you or should you not exclude stop words when you're doing the training?
So the answer to the first one is yes. If you have a large enough corpus in Spanish, you can train your own embeddings in Spanish and then compute the transformation specific to those set of embeddings, right? So, and we provide the functions. You can use text-to-vec to train the actual embeddings and then use our function to estimate the transformation matrix, right? So you can, as long as you have the corpus to train these embeddings. In terms of stop words, you mean to get those a la carte embeddings, you can exclude them, but the transformation matrix itself will actually do a lot of the work for you. If you don't exclude them, the transformation matrix will do a lot of the work for you, such that it pushes essentially these stop words out of the sort of nearest neighbors of that sense of the word.
Elliot Ash asks, does using glove or word2vec or another embedding model matter for your results? Does using different contexts, for example, longer or shorter windows, following syntactic dependencies rather than word order, make a difference?
So we haven't tried this with word2vec yet. In principle, this should be equally applicable to word2vec, and it should also be applicable to other embedding models. Indeed, one of the what we plan to do is also apply it to fast text, which would allow us to sort of make the use of this broader. So there shouldn't be any problem to using other embedding models. In terms of the size of the window, we'll notice that in that last application, the size of the window was the full response, right? The open-ended response. So these could have been lengthy responses and shorter responses. So ultimately, and we still got very sort of meaningful results from applying a la carte to those open-ended responses. So, there will come a point where if you use the whole document, presumably the embeddings will lose, the a la carte embeddings will lose meaning, but within a sensible range, you should be fine. In terms of word order is just within the, I forgot that one, in terms of word order, within the context window, word order is ignored, right?
Hauke Licht, I certainly hope I pronounced that name correctly, asked two questions, and they're pretty involved, so I'm just gonna ask one, let you answer, and then ask the other. So when relying on context words to compute the ALC embedding of a focal word, you propose to use pre-trained word embeddings and a pre-trained transformation matrix A. Once pre-trained, both are fixed. So while you motivate your paper by pointing out that the meaning of a word varies across context, you assume that this is not the case for context words. So question one is, do you think there are practical scenarios where researchers might find this assumption to be violated, as for example, when using glove for computing LCA embeddings in Rodman's corpus that spans 150 plus years?
Yes. So we do apply this to the Rodman corpus, and again we find that based on the gold standard that she proposes in the paper, we find that a la carte embeddings actually map this gold standard very well as well. So it has high correlation performance as high as what sort of the methods that the chronological method that is proposed in the paper. And we also, not only that, find that the nearest neighbors of these embeddings using a la carte, again, based on this corpus, which I should say has very few instances of the words that we're interested in. It's a very, the corpus is relatively small. The nearest neighbors that we get using a la carte are much more sensical than the nearest neighbors that we get by using the proposed sort of chronological approach. So even in that case, we found using these pre-trained embeddings to be very useful. That said, it can be argued, as you suggest in the question, that in some instances it doesn't make sense, right? So if you have a large enough corpus and you believe that it just doesn't make sense to use GloVe pre-trained, right? Because these were trained on a Wikipedia 2014, for example, right? You should probably train, your own embeddings model and then compute the A specific to those embeddings, as we did in that application where we used Empire, where again the time range was between 35 and 2010. So we had a large enough corpus, and then two, it made sense to estimate the embeddings specific to those. So there are instances in which it makes sense to not rely on these pre-trained embeddings and pre-computed A.
Well, so question 2 is essentially when do you the question as written is, if so, would you recommend a researcher to use your approach or not? But I think a more subtle take on that question is, how do you know, right? How do you know when to do one or the other?
Yeah, I don't think there's a hard cut rule in terms of when to use one or the other. As I said, we get even when applying it to the New York Times corpus used in Rodman, again, which spans many years, many decades, we got very high correlations with the gold standard and got very sensical nearest neighbors, more sensical than with the proposed approach. But I don't think there's a hard-core rule when you should use your own embeddings and not. If you have a large enough corpus, I'd say this: if you have a large enough corpus and you have some sense that applying GloVe pre-trained doesn't all make sense all that much, right? The sensors contained within the corpus that was used to train GloVe don't really contain the sensors of the context words that you're interested in. Then go ahead and train your model and compute the transformation matrix for specific to those embeddings. If you don't have a large enough corpus, right, and you still have the problem that GloVe doesn't really, you don't think that GloVe applies, you can try it out, see if it makes sense, right, the nearest neighbors that you get. And then finally, if you don't have a large enough corpus, but GloVe does fit the bill, as we show in a separate paper, that GloVe, for example, does fit the bill for many political science corpora, then just go ahead and use the pre-trained embeddings and corresponding A. So there's unfortunately, there's not a hard cut rule for this. Common sense, I guess.
Elliot Ash asks, what is gained by framing word shifts as the norm of beta hat rather than averaging the embeddings across groups and computing the distance between the averages?
Well, so what is gained is used, so the norm is just a way of summarizing this, right? So instead of, sorry, can you repeat the quote? Because I don't know if at the end, so they suggested something else, right?
Computing the distance between the averages.
Yes. So yeah, computing some cosine similarity between these averages. Yes, you can do that. The regression framework just puts it in a framework that, one, is familiar. Two, it's very easy to do these, permutation and bootstrapping. Again, that would be easy also if you're just taking averages. I mean, ultimately, you're right, it is essentially just taking averages. That's all. Regression is just in and of itself, it's just conditional expectations. So you're right that it's just taking averages over these groups. This is just one way of framing it in a way that is very familiar to understand, shifts or effects, and to understand inference that is familiar for social scientists. But ultimately, again, the intuition is correct. These are essentially, we're just using regressions to take averages of instances over various group indicators, which is ultimately what regression is.
So a question from Ian Magnuson. How much do you think the approach for learning contextualized embeddings is sensitive to how well the original pre-trained embeddings fit the domain of the small corpus. That is, if we wanted to use this approach on a small corpus, which is written in a dialect with little existing resources, no large corpuses to learn static embeddings, let alone using pre-trained embeddings, would that risk making spurious connections based on out-of-domain pre-trained embeddings?
Yeah, well, again, this relates to one of the previous questions, right? Which is when do pre-trained embeddings make sense, and when does it make sense to estimate our own? In this particular framing of the question, you're saying that there's not a large enough corpus to train your own embeddings. So again, the suggestion being you can try this to see if the results carry some sense at all, right? There must be some priors that lead you to specify the questions for this research that you can use to evaluate whether this makes any sense at all in terms of what is being captured. And if it doesn't, then obviously this, and you don't have a large enough corpus, then this doesn't necessarily apply to that particular problem. So there's the problem of just defining, when does it make sense to use pre-trained? This is not specific to this context. It's specific to just using word embeddings, right? Again, in the examples that we've done, right, even in cases where ex ante you would have thought perhaps pre-trained embeddings don't make all that much sense, right? Such as, again, the Rotman corpus that spans many decades, or other examples, we found that the results, again, correlate well with these predefined gold standards, right? And so, to the extent that that is informative to your problem, hopefully that helps.
Rick McAlexander asks, if we are comparing two different corpora, is there a multiple comparison problem whereby we may find statistically significant differences between word embeddings simply because there are so many comparisons to make?
Can you repeat that?
If we're comparing two different corpora, so for example, I will editorialize here. In your examples comparing Democratic versus Republican corpora, is there a multiple comparison problem whereby we may find statistically significant differences between word embeddings just because there are so many comparisons to make? So in other words,
yes,
are 5% of them spurious, and that's what you get,
Yes. So, well, I mean, ultimately, again, that's why we use the permutation test to build a null, which might be either too liberal or too conservative, but ultimately allows us to try to minimize that problem. That said, it is the case that you can end up with spurious results, just as in any other application. So, yes, there is a problem. I think the problem is not so much on the side of when you have a lot of instances of these words in both corpora. I think that's less of a challenge or of a problem to make spurious inferences there. Rather, the problem is more on the lower end when you have very few instances of each of these words or of the target of interest in the two corpora. So when you have very few instances, that's, I think, where spurious inferences can be particularly problematic. Again, that said, one advantage of a la carte is that it does create meaningful embeddings of words given few instances of the words. But in the context of few instances of the word, you should be careful with these spurious inferences, as you suggest in the question.
I mean, you kind of, or at least I kind of think of the comparison of what you're doing to like genome-wide association studies, where they're trying to figure out what genes cause some disease or whatever, and you just get zillions of comparisons, and of course a lot of them are going to be spurious. You might be able to adapt some of the methods that work for that to this.
Yeah.
I don't think you'd want to use a Bonferroni correction, right? Because then you're going to find nothing because you're doing hundreds or thousands of comparisons. You may want to use something like the false discovery rate.
Yes, that's a valid point. Yes. Yes.
Okay, so I think we have time for two more questions. I'm going to ask one from the audience, and then I'm going to ask one that I had. So Lisa Zenter asks, did you lowercase during preprocessing? I realize there's a huge difference between capital T Trump and lowercase t Trump, but in Table 3, other names like Clinton or Barack are displayed in lowercase. For English, it's probably not that important, but in German, for instance, there is a difference in meaning depending on being lowercase or not.
Yes. So in that example, we use pre-trained glove embeddings, right? But so what we do is in the New York Times corpus, we identify the uppercase Trump as uppercase, so just using uppercase. So we don't lowercase when we identify the context of that word, but then we do lowercase the context words, right? And the reason why we do this when we actually find the embeddings of these words is because glove is lowercase. So glove pre-trained is lowercase. So when you find the embedding, you won't find the embedding of Apple with uppercase, you'll find it with Apple lowercase, right? And so that's what we do when we find the embeddings. But to identify the instances in the corpus, the way that we distinguish Trump as lowercase Trump is if we don't lowercase to do that. In the case of Clinton, similarly, we identify Clinton with uppercase T. When we do the a la carte embedding, yes, we lowercase. Now, in the case of German, you would use German-specific embeddings, of course, and your corpus, whichever corpus that you have for the contexts. And so, as long as the embeddings, right, of the words are uppercase or lowercase, right, just be consistent with that, and that's fine, right? As long as you're consistent, that's not a problem. So, yeah, that wouldn't be a problem.
So my question is, if we're just looking for essentially disproportionate instances of contextual words, this is probably not that big of an issue. But if we're trying to actually impart semantic meaning to the target word, so in other words, we're trying to like identify a valence dimension or something for a target word in one instance versus another. I'm curious about. In actual language, there are ambiguous or disputed meanings, right? And you see this all the time.
Mm-hmm.
As a simple example, is a particular word or a particular phrase, is it racist or not? Right? You will get very different reactions from different people, even though they may even be superficially similar. And I'm not sure there's an actual ground truth there. There can also be cases where the meaning is ambiguous, right? You think about dog whistles, where people are using phrases and words that have plausible deniability, right? They have ambiguous meaning and can be heard differently by different audiences, and the reason that you do it is because it's genuinely possible to not intend some sort of sotto voce interpretation. So if we're going to try to use context to figure this out, is it possible, or how can this method recognize that kind of ambiguity?
Well, so I mean, ultimately, the method will rely on the data that you feed it, right? So if this data captures that ambiguity, in other words, and that ambiguity has to be captured in terms of just differences in the context words that are used around whatever phrase is of interest or target is of interest. If there are differences in those context words, then this method will essentially capture those, right? And then the subsequent question would be, well, do those differences capture something more meaningful, like say racism or whatever not that you want to quantify? But ultimately, it'll rely on the data that you feed it. So potentially, it's not a question so much of the method itself, but how you acquire that data. So, for example, differences in how you and I understand a given word, potentially the way that we could capture that is, well, ask us both to use this word in context. Give us 10, 20 instances of this word in context, right? Then we can use that to apply this method, right? And then again, ultimately that will just capture differences in those contexts. Are those differences meaningful in terms of some sort of more meaningful qualitative sense, like racism or so forth? That's a qualitative type question that is easier to answer when you look at, say, the nearest neighbors and so forth. There's all ultimately more of sort of a discovery qualitative type method. But yeah, I'm not sure if that answers your question, but I think there's an interesting challenge to actually get good data to capture that. I think it comes from getting the data rather than the method.
Well, we're at 1 o'clock Eastern, so I'd like to thank Pedro for being our presenter this week. I want to remind everyone that the presentation will be posted to our website shortly after the broadcast if you'd like to share it with a colleague or watch it again later. I also want to invite you to join us on not April 2nd, but April 9th, when we will host a talk by Josef Woldens, I hope I pronounced that correctly, from the University of Minnesota. He's giving a talk entitled Interviews Are Not Small N Surveys, Upending Assumptions for Better Interview Sampling. Please see our website, www.methods-colloquium.com, for more information about this talk. Pedro, thanks very much for being here today.
Thank you again, Justin, for the invitation, and thank you all for the excellent questions. It's been great. Thank you all.
And I hope to see you next week.